Okay, so we're going to be talking about epoxy resins. So epoxy resins are pretty much exist as polymer matrices. So they are used with fibers to link them together, like carbon nanotubes and cellulose nanocrystals and stuff like that. Some of the significant properties of the material are it's curable, and based on the temperature at which you cure it, like it ranges from 5 to 150 degrees centigrade. It makes it highly resistant to environmental degradation, water degradation, chemical resistance, as well as it gives us some electrical and thermal insulation. It's highly adhesive, so it's used as adhesives in aircraft, structural for to make to link together structural parts in aircrafts and a lot of things like boat making in automobiles. It has high temperature resistance and it has lower shrinkage when cured. Some of the typical applications range from aircrafts, automobiles, boat buildings. They're even used in ICs where like the small dot there. So those things prevent it from water, air, and it gives us chemical resistance to the ICs. And over here is those pipes which are coated with epoxies. So epoxy paint and emulsions are pretty common because it gives you high thermal stability. At the same time, it's corrosion resistant. These are some of the numbers I got for standalone epoxy without any reinforcements in it. They mentioned it with some post curing period, but there also exist. I mean, they have similar numbers even without post curing. Yes. So these are some of the book properties for epoxies. So the tensile modulus is around like 10,500 Newton per millimeter square, which is, and the properties kind of match with what we get from the additive manufacturing. So this is in newtons per millimeter square, so that was in newtons per meter square. So one of the most common manufacturers for epoxies is Dow Corning. They have like 20 grades of liquid resins, and different types of emulsions and other reinforced epoxies as well. It's pretty cheap. It's not that costly. I guess it comes around like $50 or something. Depends on the grade too. This is not actually more. This is more like a news blog rather than actually a case study, but it was pretty interesting. So they already use it for windmills and stuff because they've been trying to use carbon nanotubes as and carbon fibers for windmill blades. And usually in windmills they use this balsa wood which they export from Cambodia or someplace. So it's really high. It has really high strength, but it's very light. But then it cost them a ton to actually export these back. I mean, to build them. So instead, they tried to do with 3D extrusion printing, where they used a honeycomb structure for epoxies with carbon fibers. So one of my case studies for it is rubbery and glassy epoxy resins. So they cure it with different types of different curing agents, and they get rubbery epoxies and glassy epoxies, and then they reinforce it with carbon nanotubes, and they check for the mechanical properties of those, the properties, I mean, of the epoxies. So the first one is with D2000, which is one of the curing agents which they use, and it's a pretty big epoxy name, so I didn't include it. So I just included that it's EPON 828, which is like the commercial name for it. The difference between the two, which makes it rubbery and glassy, is because of the glass transition temperature. So one is like subambient at room temperature, while the other one goes about like closer to 80 degrees centigrade. So the 80 degrees centigrade gives you like a glassy epoxy, while the other one gives you a rubbery one. These were TEM images of carbon nanotubes reinforced with the in the epoxies. So the top two represents the glassy one, sorry, the rubbery one. The bottom two is the glassy one. The small white dots which you find in the I mean in the structures are the carbon nanotubes. They just add around like 1% weight to it. This figure just shows that it gives you like a homogeneous distribution, and that when they do tensile stress, it breaks and it doesn't actually stretch, and you don't have to pull it out. So that gives you like some strong interfacial bonding both in the rubbery as well as the glassy states. These were some of the numbers which they got. Um, However, even though it does have a homogeneous distribution, the rubbery one has had an increase in its tensile modulus, while the glassy one had a small reduction in the tensile modulus. You can see, like glassy has a comparatively higher modulus than the rubbery one, but still, when introduced with carbon nanotubes, it actually reduced its properties than actually enhance it. The first two graphs actually show the stress and strain percentage for the rubbery one on the left and the glassy one on the right. They also did an impact strength to see how exactly impact strength increases for the epoxy without any reinforcement, and then with nanotubes, and then with functionalized nanotubes. So functionalized nanotubes is trying to dissolve the carbon nanotubes in an organic solution in order to get a uniform coating so that it disperses well inside the polymer matrix. The next one is again a reinforcement, but this time they use cellulose nanocrystals. So these cellulose nanocrystals actually increase the properties of epoxies to a great extent when compared to other things which have actually been reinforced with epoxies like graphene and all the other things. I'll show you the graph in a few minutes. So they do a lot of testing with it. They do flexural testing. They do mechanical dynamic analysis. They do a lot of viscosity tests and also tensile tests. So the main thing was to actually identify what percentage of cellulose nanocrystals they can introduce into the epoxy in order to get good values for mechanical strength. At the same time, not lose the properties of the polymer as well, like its viscosity and things like that. So they tried different percentage volumes like 0.5, 1, 2, and 5. It was seen that till 2% was fine, but 5% was the limit after which you did not actually have homogeneous distribution in the polymer matrix. And when they introduced the cellulose nanocrystals into it, there was not much change in the viscosity. It was very mild change in viscosity. So the polymer and the glass transition temperature and the polymer properties retained. So they were able to get the polymer properties at the same time some enhanced strength and mechanical properties. So these were some of the numbers which they got for tensile, Young's modulus, and elongation for different percentage of CNCs which they added. And the table on the right actually shows a comparison between other reinforced fibers like graphene nanofiber, carbon nanofibers, carbon nanotubes compared to cellulose nanocrystals, and it's seen that cellulose nanocrystals has much more greater enhancement in mechanical properties as compared to the other reinforcements. So these are my references.